Assalamualaikum. My name is Hafiz, Waleed Zahid, roll number 21 TE83. Today we perform lab 8 of digital signal processing, moving average filter, FIR filter, Fourier transform design methods. In task 1, define filters. Filter is a device or process that removes unwanted components or features from a signal. In signal processing, a filter can selectively allow certain frequencies to pass through while attenuating others. Filters are essential in various applications such as audio processing, communications, image processing, and control systems. Types of filters. Filters can be classified based on their frequency response characteristics and the domain in which they operate. There are some types of filters: low pass filter, high pass filter, band pass filter, band stop filter, and all pass filter. Low pass filter allows frequencies below a certain cut of frequency to pass through while attenuating other frequencies. A high pass filter allows frequencies above a certain cutoff frequency to pass through while attenuating lower frequencies, and band pass filter allows frequencies within a certain range to pass through while attenuating frequencies outside the range. Band stop filter allows frequencies within a certain range while allowing frequencies outside this range to pass through, and all pass filter allow frequencies to pass through but alters the phase relationship among the frequencies. What are the all time domain parameters of a filter? Time domain parameters describe the filter's behavior: impulse response, step response, group delay, phase delay. In impulse response, the output of the filter when the input is an impulse signal. In step response, the output of the filter when the input is a step signal. In group delay, the time delay of the amplitude envelopes of the various spectral components of a signal as they pass through the filter. And in phase delay, the delay experienced by the sinusoidal components of the input signal. The next one is, what are the frequency domain parameters for a filter? Frequency domain parameter describe the filter's behavior in the frequency spectrum: frequency response, magnitude response, phase response. Frequency response, the filter's output spectrum in response to an input signal spectrum. It includes magnitude response and phase response. The next one is cutoff frequency. Cutoff frequency is at which the filter's magnitude response starts to significantly attenuate the input signal. Bandwidth, the range of frequencies that the filter allows to pass through the minimum attenuation. Stop band attenuation, the level of attenuation applied to the frequencies in the stop band. In E part, discuss the role of low pass filter for filter designing. Low pass filter plays a crucial role in various filter design applications due to their fundamental properties: signal smoothing, anti-aliasing, communication systems, control system, biomedical applications. In signal smoothing, low pass filter remove high frequency noise from signals, making them essential in applications like audio processing and image enhancement, or anti-aliasing. In digital signal processing, low pass filter are used before sampling to prevent aliasing, which occurs when high frequency components fall back into the lower frequencies. In communication system, they are used to limit the bandwidth of signals to match the channel capacity and reduce interference. In task 2, apply 3 tap, 11 tap and 25 taps critically around moving average filters on signal X noise, and observe the time frequency and domain parameters. So this MATLAB code provides calculate and plots the frequency responses of 3 tap, 11 tap and 25 tap moving average filters. It first defines each filter's coefficient using the ones function, normalized by the number of taps, 3, 11 and 25 respectively. The frequency function is then used to compute the frequency response of each filter, which returns the frequency response H and corresponding normalized frequencies W. The plot displays the magnitude of these responses, showing how the filters attenuate or pass frequencies. Especially the moving average filter's low pass characteristics becomes more pronounced as the number of taps increases, leading to better attenuation of high frequency components and a smooth filter response. This illustrates the trade-off between filter length and frequency selectively. Longer filters provide sharper transition between pass band and stop band. This is the output of this code. In task 3, Calculate the filter coefficients for a 3-tap FIR low-pass filter with a cutoff frequency of 800 Hz and a sampling rate of 8000 Hz using the Fourier transform method. Determine the transfer function and difference equation of the designed FIR systems. Compute and plot the magnitude frequencies response. So this is the MATLAB code. In this code, designs and plots the frequency responses of FIR low-pass filter with varying number of taps 7, 17, 51 and 101, all with a cutoff frequency of 800 Hz and a sampling frequency of 8000 Hz. Each filter is designed using the FIR1 function where the filter order is 1 less than the number of taps. The frequency function is then used to compute and display the frequency response of each filter in a separate format, allowing for a visual comparison for their characteristics. As the number of taps increases, the transition band between the pass band and stop band becomes narrower, and the filter's ability to attenuate frequencies beyond the cutoff frequency improves. This highlights the trade-off between filter complexity and performance. More taps result in better frequency selectivity and sharper cutoff characteristics. This is the output of this code. In task 4 and last task, calculate the filter coefficients for a 5-tap FIR bandpass filter with a low cutoff frequency of 200 Hz, 2000 Hz and an upper cutoff frequency of 2400 Hz with a sampling rate of 8000 Hz. Determine the transfer function and plot the frequency responses with MATLAB. Okay. This MATLAB code designs and plots the frequency responses of FIR bandpass filter with a different number of taps 7, 50, 7, 17, 51 and 101. The filters are designed to pass frequencies between 2000 Hz and 24 Hz using a sampling frequency of 8000 Hz. The lower WC1 and upper WC2 cutoff frequency are normalized with respect to the Nyquist frequency. Each filter is designed using the FIR1 function specifying the normalized cutoff frequency and the bandpass option. The FIR1 function creates an FIR filter with n plus 1 coefficients where n is the filter order. The frequency function computes and displays the frequency responses of each filter, plotted in subplots for easy comparison. The subplots show how the frequency response of the bandpass filter changes with the number of taps. Filters with more taps exhibit sharper transition between the pass band and stop band and better defined bandpass characteristics indicating improved frequencies. This is the output of this code.